Hello class, we're doing lesson number 6 in chapter 11, more on multiplication. And I know we've been having quite a lot of fun with our fractions in this lesson. And we're going to have a lot more fun here because we're just going to make it that much more complicated. I think that when we start getting into these types of multiplication problems with fractions, that they're actually a lot more difficult when we're dealing them, I think, with numbers. Then, when we look at the algebraic equivalent of algebraic fractions, okay? So, let's just go ahead and take a look. A dollar bill isn't as large as it used to be. In 1929, the dimensions of the U.S. currency notes were reduced from 3 inches by 7 and 1/2 inches to, I'm sorry, it's 3 inches by 7 and 1/2. So let's just draw that up here on the board. Ooh, let me get my pen. So let's just go ahead and draw up that diagram so we can see it. We're going to have 2 of them actually. In fact, I can probably just go ahead and make a couple of little rectangles here. We have this one, and then we're going to have one that's like slightly less, okay? And we're told that it was 3 inches, and again, this is probably not to scale, because I wasn't attempting to make it to scale. Make it a little thicker. So this is 3, and that's 3 inches, right? And this is 7 and 1/2 inches. Okay, so that would be inches. So picture that being a dollar bill. And now they reduced it to 2 5/8 inches. Okay, and to 6 1/8. Okay, so again, not to scale, but it just kind of gives you an idea of there's a reduction. Okay, now this cartoon was one that many appeared in the editorial pages of the nation's newspaper at the time. Okay, and it was showing that you have the big dollar bill. I guess this lady was a little heavier, bigger, and now Uncle Sam was more. They found that the smaller bill was more attractive, let's just say. Okay, an obvious advantage of the smaller size is that less paper is needed to produce each bill. Because the dimensions of the larger bill were 3 inches by 7 1/2 inches, it required, okay, that 3 times 7 1/2, and we do all the math there. What do we end up with? 22 1/2. Okay, so why did they do this math? Well, remember that 7 and 1/2 is really 7 plus 1/2, so they did the distributive rule, multiplied the 3 times the 7, got 21, and then 3 times 1/2, and we were able to get to 3 halves, and 3 halves is really 1 1/2, so it's 22 1/2. So that's how much you needed in square inches of paper. Another way to make this calculation is to write 3 and 7 and 1/2 as fractions before multiplying. Well, we could have created that by making them fractions, and we can see at the top that they made 3. Let's go ahead and write that. 3 times 7 and 1/2. Well, that would be equal to 3 over 1 times, and we know that this would be 15 over 2, because I multiplied 2 times 7 plus the 1. 2 times 7, it's 7. That's 14 halves. 14 halves plus 1/2 is 15 halves. So I can go ahead and do that multiplication. 3 times 15, and what do I get is 45 over 2. And then I can just turn this into a mixed fraction, 22 over 1/2, 22 and 1/2. I'm sorry. Now, the two methods that we have just used also, the two methods that we have just used can also be applied to finding the amount of paper in the smaller bill. Now, treating each dimension as a binomial. Okay, so we'd have to go ahead and do all of this wonderful math. We have 2 5/8 times 6 1/8 we would have 2 plus 5/8 times 6 plus 1/8. So now what do? Well, remember we used to have that wonderful little FOIL method, right? Well, that's all we're really doing here, right? We're going to end up with 2 plus 5/8. This is the smaller one, remember. And we have 6 plus 1/8. So what are we going to do? Well, 2 times 6, right? So let's do that. 2 times 6 is 12. Then we have, let's see, they took the next one and did 2 and 1/8. So they did the first and then the outer plus 2 and 1/8, right? Okay. Or, excuse me, 2 times 1/8. That isn't 2 and 1/8. We're not adding them. So 2 times 1/8. All right. And then we're going to multiply the 6 times 5/8. And again, remember, we're multiplying these. These are fractions that are being multiplied, not added. And lastly, we're going to end up with 5/8 times 1/8. So 5/8 times 1/8. Okay. So let's do our math here. We'll end up with 12 plus, well, what do I have here? I have 2 8s. 2 times 1/8 is going to give me 2 8s. Plus, I'm going to end up with 6 times 5, which is 30 over 8. Plus, now I'm going to multiply these, and I'm going to have 5 times 1 is 5, and 8 times 8 is 64. So, look at what we have now. Well, we've got an opportunity to add these two together, and that will give me 32. So let me just put that as 12 plus 32 eighths plus 5 64ths. Now, as you can see, we still have quite a bit of work here because we do not have common, well, actually, not that we don't have a common denominator, but we do have actually an opportunity to express this as a whole number. So we have 12 plus 4 plus 5 over 64, right? And when we add 12 plus 4, we end up with 16 plus 5 64ths, and that would really just be 16 and 5. I'm sorry, I wrote 16 there. That's 64 and 5 64ths. So now we can see that that changing our each dimension to a fraction before multiplying, okay, we end up with 16 and 5 64ths square inches. So this is what we had here versus this. So now we can see sort of almost apples to apples, the difference between the two. We can see just alone 6 square inches, but this is 1/2 and that's 5 64ths. We can actually subtract these just by creating a common denominator between the halves and the 64ths. And I could just suggest to you that 32 over 64 would be 1/2. So 32 over 64 would you could subtract 5 64ths, and let's just do that over here. Now they didn't necessarily do it, but I think it's a good opportunity. So we would have 22 and 32 64ths, which is 1/2, minus 16 and 5 64ths, and I subtract 16 from 22, what's that, 6, and I subtract the 5 from the 32, and that'll give me 27. So really the difference, this is how much they were saving in paper in square inches, okay? 6 and 27 over 34. That's very close to like 6.5 square inches. Now imagine that for every dollar bill, or every bill that's printed, whether it's $1 or a 5 or a 10 or whatever numbers they had, whatever denominations they have. Now, now we can see here in making calculations that both integers and fractions, it's helpful to think of the integers as fractions whose denominators are 1. Okay, the product of the polynomial of a polynomial and a fraction can be found by the same procedure. The polynomial is first written as a fraction whose denominator is 1. So we can see an example here. We have find the product of x plus 2 and x over 3. Well, they just simply put the x plus 2 over 1 and multiplied it by x over 3. And then you can just go ahead and do your multiplication. X times parentheses x plus 2 and parentheses over 3, right? And if you multiply that, you'd end up with x squared plus 2x over 3. Now, for many purposes, very important here, for many purposes, it is more useful to leave an expression as x times the binomial, excuse me, x plus 2 in factored form rather than carry out the multiplication. Now the reason is, again, I mentioned that before, is if you tie that all together and you express it as x squared plus 2x, you might lose the opportunity of a factor that could be canceled out, especially as it works in other problems, because you may have problems that have levels of steps. You may be finding something here so you can plug it into something else. So it's sometimes better just to leave it separated like that, x times the binomial, x plus 2, so that when you plug it into the other part of the problem that you're solving, you might see, oh, here's a great opportunity to eliminate. Okay, so let's take a look at example number 2. Find the product of 4x and 4 over x minus 1. Okay, I think we're going to have to clear the board on this one. Let me just pause for a minute. Okay, I cleared up the board, and let's go ahead and do example number 2. Find the product of 4x and 4 over x minus 4. So 4x and times 4 over x minus 4. Oops, sorry, there's a minus there. Okay, now we can go ahead and express this as 4x over 1 times 4 over x minus 4. All right, and if we did our math, we're simply going to be left with 16x over x minus 4. So there's really not much we can do here. There's nothing. These are again, this is one term all to itself, x minus 4. So we really couldn't eliminate the x there. The next pair of examples show how the product, such as x plus 1 over x times x plus 5 over x, can be found in different ways. Okay, so we're going to take two approaches here. Let's just go ahead and clear this out. See what they do. And again, when they say there are a couple approaches, really with math, sometimes you have many approaches that you can take. You're generally trying to find the easiest one. Now, so we have x plus 1 over x. Oops, just write that, x plus 1 over x. And we're going to put parentheses, and we're multiplying this by x. Boy, I keep making a little marks here. Alright, so we have x plus 5 over x. Okay, so we know that we can apply that FOIL method. What are they doing? They're saying, well, x times x is x squared, right? So we took x times x. Then they took, that's plus x times 5x. They came all the way out here. So x times 5 over x. Then they took the x times 1 over x over here. X, I'm sorry, I should have written that as just a simple x. But that's all that is, just a big x here. And lastly, we took x over 1 over x times 5 over x. So you could see that we have some complexity to deal with. This is a plus, plus, plus. So now we can just go ahead and start recognizing really from the bat that there are going to be some things some opportunity to eliminate, but let's go ahead and write it out. X times 5, 5x over x, plus we have 1 times x over x. Let's do it as they did. It's just basically x over x, plus now we have 5 times or 5 over x times x, which is x squared. But let's see what we have here. What do we have? Well, I have over here the opportunity to eliminate these two x's. They're both factors. In fact, I can eliminate these two as well. So I really end up with x squared plus 5 plus 1 plus 5 over x squared. Now, I'm going to simply add these and say x squared plus 6, that's 5 plus 1, plus 5 over x squared. Okay. Now, we weren't told to express this as a fraction. We simply used our FOIL method as you know, they wanted to use this method. But if we go down below, we can see that what they did was they put it all together, and it's different. We're going to go ahead and multiply and create a similar denominator. Let's see what they did here. It's very interesting what they did, and you're going to get a different answer, though. It's really the same answer. It just comes out in a different form. Remember, we have here, this is expressed as the sum of various terms. Our answer in our next one is actually going to be a fraction. Okay, and again, depending upon what you're looking for and what you're trying to achieve, one may be better than the other. Okay, so let's go ahead and see what they did here. We have x plus, I could probably left that up there, but we have x plus 1 over x. Okay, and we're going to multiply this whole thing times x plus 5 over x. Now the first thing that they did was they convert. They're going to multiply. Well, the first thing they did was they changed the x into a fraction of x over 1. So that's just to make it easier to see. Okay, so we have x over 1 plus 1 over x. And we're multiplying that by x over 1 plus 5 over x. Now, by doing this, we can see that we can now convert, I'm sorry, let me close that. We can convert these into fractions themselves. What do? Well, we can multiply this by x over x, right? Which is the denominator here. And we can multiply this also by x over x. Remember, x over x, I'm multiplying by 1, so I'm not changing values. So what do we have? Well, we end up with x squared over x, right? Plus 1 over x. And the same thing over here. We're going to end up with x squared. Sorry, my 2 didn't come out properly here. Let's try that again. X squared over x plus 5 over x. Okay, so we know we can now express this as x squared plus 1 over x, right? And we can express this as x squared plus 5 over x. I'm sorry, I should have just made that there. Okay, so having now this, we can also, I'm sorry, now we can actually multiply these two. Okay, now if we multiplied them, it would look something like this. X squared plus 1 times x squared plus 5, and what's x times x? That would be over x squared. Okay, so we have now x squared plus 1 as a binomial, and we have x squared plus 5 as a binomial all over x squared. Now if we multiply this out, we would end up with this expression. It's x to the 4th power plus 6x squared plus 5. They kind of just jump to that. We would have done our math, and we would have just done, FOIL again. This times this, and this, and this, and we would have gotten this. So this would have been our answer. And you say, but that looks completely different from the last one. Well, it does, simply because if we would look back, and it says here, although the answer to example 4 looks different from that example 5, the two are equivalent. Why? Because if we were to convert, well, actually, if we were to just go reverse, let's reverse this and say x squared, x to the 4th over x squared plus 6x squared over x squared plus 5 over x squared. So we're just distributing that x squared underneath. We're just writing this out as the sum of these different fractions. We could now simplify and get x squared plus 6 plus 5 over x squared, which is the example number 3. That was the answer. So you can see that both expressions are equivalent. It just depends on how you wanted it and how you work the problem out. So, okay, that is the end of lesson number 6.